Screencast people, you missed about 30 seconds. Okay, so the question was, hey, can we use multiprocessing from threading? The answer is you kind of have to be careful. The best I could find was this Stack Overflow answer, which basically said, look, you can use fork in a multi-threaded program. And then what does that actually mean? It means that both copies of when you forked, now both processes have threads associated with them. So something's got to be, you've got to have some way of dealing with that. But in the sense of being able to do it, the biggest thing is after you do fork and before you do exec-vp, don't do any malloc, free, new, or delete. And that was the best I could find. And said, look, you can do it. Just don't do anything that's going to mess with memory in such a way that it will end up being like, it'll end up messing with the schedulers and things. And that was the best I could find. So the answer is yes, if you want to use multiprocessing from within multi-threading, you can. You just have to be a little careful about it. And obviously, testing is always going to be something important to do. Okay, so good question. And there's the kind of the answer that I could find. Feel free to do some more digging on your own. But it is possible. It's just you got to be careful. Okay, so let's move on to network system calls, library functions, etc. Now, as I said a couple minutes ago, this is where I think it's kind of a flashback to CS 107 because some of the wonkiness associated with C propagates to these functions that are about getting host names and resolving them and using these low-level functions to do so in a way such that you can support IP version 4 and IP version 6 and any other version that you want. It turns out that socket programming, which is what we're talking about here, where two computers talk to each other through a socket, or basically a port, a socket is, as it turns out, just a file descriptor, but it's a very special file descriptor. It still gets an entry in the open file table, believe it or not. It still gets an entry in the file descriptors for a particular process, but it allows you to have a double-ended communication between two processes or two computers over a network. Okay, so it's just like a file descriptor, but there's a little more to it, and you don't necessarily need to know what else there is to it, except for the fact that even though it's a file descriptor, you actually can't say, you don't say read and write in the same way that you normally do. Okay, you use things like accept, and you use other functions that I guess you can use write on the file descriptors, but you can't. But there's some other nuances that you can't just say, oh, it's just like every other file. Somewhat like every other file, but not exactly. So let's talk about the specifics. Because we are people, we like to use things like www.facebook.com versus 31.13.75.17, right? You don't want to memorize numbers. We've talked about that in a number of different ways this class. And so there are functions that will get the number from the name. So if you know the name, www.facebook.com, which you can remember easily, you can use a function called getHostByName, and you can also use one getHostByAddress, which they're both technically deprecated. In other words, there's other things you should probably use instead. However, your book talks about these ones, and they're still used enough that you should be used to using them. In particular, I'm not exactly sure what the actual new one is. I see these ones more than I see that, and I forget what the actual, the one that you should use these days is. So anyway, we're going to talk about these two. And what they take are a getHostByName takes a name, like www.facebook.com, okay, and it returns this struct called host, a struct host ent, which is a particular struct we'll see in a second. And it populates it with the information you're going to need about like what the IP address is and so forth. You can also pass in an address here. As it turns out, I don't believe that's actually a char star, although it looks like a char star. You have to actually cast it to, believe it or not, like an int in this case. And the reason for that is because you need to, actually this one maybe not. This one, I don't use this one. I don't even think we use this one in an example. This one, maybe not. There are ones where you have to do that. And again, it's because of the wonkiness of C, and some of this stuff was done in 1977, and there weren't even void star pointers then. So everything became a char star pointer, and you can do that. In this case, I guess, in this case, yeah, this is actually going to be, I believe, a number, a pointer to a number, and you're going to say how many bytes it is, and then another variable that talks about the type of connection, whether it's an IPv4 or 6 or so forth. Okay, so there's lots of details about that you have to know when you're using that function. Okay, a struct host ent has the following, well, we'll get to what it is. Let's see, get host name. Yes, here we go. This one is a struct inaddr, which happens to be an int. It's the weirdest struct I've ever seen. It's got one value in it, which is an int. So we'll see a little bit more about that in a second. But the one we're going to focus mostly on is get host by name, as it turns out. Okay. All right. So what is this? Oops. Oh no, that's not what I want to do. Hang on. I don't have my tablet set up quite correctly now. So hang on. Let me go back here, and we will use cursor. There we go. Okay. All right. So here's what the struct host ent looks like. Okay, first of all, it takes inside of it, I will use the pen, it takes a struct called struct inadd_addr, which is, in this case, an unsigned int, saddr, which is, like I said, the strangest struct because it's only got one value in it. And you normally don't bother with a struct that has one value in it. What's the point? Maybe this is for, hey, they thought maybe it would be used some other way, and they might have some other, they probably were forward thinking enough, and it never has changed. So that's all it is in there, okay, is an unsigned int. And then the struct host ent has a regular old char star. Finally, we get a regular old char star, which is the name. Okay, that's the official name. Turns out, and I'll show you an example, the official name might be different than what you actually type in. A lot of times they end up going to the same IP address, but the name could be a little bit different. Then you have a bunch of aliases, okay, and the aliases are other strings that also refer to the same IP address, okay? So there's like an official one, and there's other ones that do that. You rarely see the aliases one filled in at all. I guess maybe it doesn't really, nobody really cares that much about it, but you rarely see that in. But it is a char star star, meaning that it's basically just like every other char star star we normally use. It's a, as it turns out, null terminated list of pointer to strings. So string, 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 and then the final one is null. You know you've reached the end. That's what that one is. Okay. The H address type is going to be different depending on which type of IP address you care about. So in this case, we'll probably stick mostly with AFINet, which means the internet for IPv4 addresses. Okay, and this is actually somewhat important. We'll see why when we get into the details of some of the strange polymorphism that they've jammed into C, as we see. Okay, and then here is a char star star H address list, which is another not char star star. It's basically a void star star. That should be a void star star. But when they built this function, they either didn't have void star star, or they didn't want to use it for whatever reason. But when you use this, you should cast it to the appropriate thing that it is, which you will know based on analyzing this. We'll see how that works. Again, this is like really low level 107 kind of stuff. Yeah. Are these the same people who made the Durant? Probably, yeah. Probably the same people, yeah. So there you go. Yeah, it's, look, when you're designing something in 1970s, it's a little bit different than the way you might design it today, maybe. But yes, it's probably the same people who did that, or somebody who's thinking along the same lines. Okay, anyway, we'll see why this becomes interesting in a few minutes. Okay? All right. The saddr field is what we call a dotted quad, okay? Basically, it's 4 bytes. 1, 2, 3, 4, okay? 4 bytes, and this is what you hopefully have seen IP addresses that look like this in the past. If you haven't, well, that's what an IP address looks like, an version 4 address looks like, 171.64.64.136. And those IP addresses, they break them into 4s because it's a little easier than memorizing that big long number 1. And number 2, each little byte means something different. Like the 171, I believe that's Stanford's main, the first byte in all of Stanford addresses is 171, I believe. And then the other ones kind of slowly get it down to the actual machine or router that you're actually looking at. So that's how that works. Meaning that because these are just bytes, the IP version 4 address is 4 bytes long, or 32 bits, and it's 171.64.64.136. Now, what order are those bytes going to be in? In other words, when you have this is the 107 stuff I was talking about too. When you have a number in a 4-byte number on your system, there's 2 different orderings we could use. Remember what they were? Little endian and big endian, right? And our machines are generally little endian machines, meaning that the little end of the number actually comes first in memory. So 136 would actually be the first one in memory, and then 64, and then another 64, and then 171 would be last in memory. We could have done it in exactly the opposite order. You could have done it in big endian, and for those of you who took CS, let's see, 107E, I believe the Raspberry Pis are in general big endian, although maybe I think I can actually switch it back and forth as it turns out. But the point is that in that case it would be in a different order. Well, because of standardization, your computer, which is little endian, needs to talk to some computer on the other side of the world, which may be big endian. You have to make a decision on which direction to put the bytes when you actually send them over the wire. Okay, so the reason we have to do that is so that everybody can talk together. And therefore, if you have the wrong type on your computer, you'd better do a translation when you're about to send it. We will see that in action. I'm just setting you up for it, thinking about it right now. And I'm going to show you the details in a second. Okay. Let's see. Yeah. So for non-IP version 4 ones, we can also let's see. Hang on. There we go. Let's see if this works. For non-IPv4 ones, we have different information in all that thing. It's got other information in there. Adder type is going to be a different actual number. Length is going to be different. If you have 128 bits, you're going to need to report that. And the list can have different types of information too. So you've got to be a little bit careful with that as well. Okay. All right. Now, why is it not letting me do this again? There we go. Okay. Any questions on that so far? No, we're getting to the actual code here. In fact, let's actually write some code, and then I'll show you this as we go along. That is way too small. All right. So there we go. All right. Networking. Resolve hostname.cc. Okay, so you have a copy of this if you wanted to take a look and take notes. But what, it's already in here. I guess I don't need to retype it. It's already there. Let's go through what this actually is doing. This is the meat of this program that is going to let you type in a name and then get out the details of the official name and then all the IP addresses associated with it. Okay, so we have to start out and we declare a struct host ent. This is a statically built variable that is kept by the operating system. So if you're going to use this multiple times in your code, you'd better make if you want to keep track of different things, keep a copy of it, because it's not thread safe and it's other things, because you are just getting the actual pointer to the data that's living inside the function that you're calling. Okay, not the best way to do it, but that's the way static variables work, and that's how this works. Get host by name is a C function, so we need to convert. If we have a C++ string, we just convert it to C string. Okay, and then calling the get host by name will populate this. Okay, if it comes back null, it means we couldn't resolve the name. That could be for a number of reasons, as it turns out. It could be that your DNS server is down, and that's on your computer or the network or the router and so forth where you're connecting to. Or it could be some other reason. So if you type one and it happens to be not there, it doesn't necessarily mean that it doesn't exist, but it means that your program couldn't resolve it. This is the problem with networks. Sometimes other things that you can't rely on go down and nothing you can do about it. Okay, then HE, the H name is the name we talked about, and then all of those IP addresses, we just go through them one at a time by first saying, oh, okay, let's cast the H address list to what it really is, and we know that it really is a IN address double pointer. Why? Because we know we're asking for the IP version 4 address. In other words, we called get host by name, meaning we were expecting an IPv4. If you want an IPv6, there's a different function you call. Okay, and I'll show you that one in a minute. But anyway, then you get the IP address by the IP addresses by looping through until you get null. Okay, and how do we actually get out the actual IP address? Well, remember, it's just a number right now, and it's just a 4-byte number. And so what we do is we call another function called inet network to printable is basically what the NTOP stands for, which means it takes, it says, hey, what type of IP address are you using? In this case, IP version 4. Okay, it says, give me the actual pointer to the address itself. Okay, and then give me a string to populate it with, and that's what we've done up here. And we know that inet underscore addr strlen is the maximum length of a IP address, as it turns out, so we know that's okay. And then how long it is also passed in so that it won't write over the buffer. Once you do that, it takes that number and it forms it into a nice 172 dot whatever. Okay? Questions on that? Yeah.
So just making sure, AFINet is IP version 4?
Yes, AFINet is IP version 4. Let's look real quickly. Resolve hostname 6.cc. Yeah, there's the one for IP version 6. AFINet 6, etc. And we also would call a different function called getHostByName2. They weren't very clever when they named these, I guess. You'd think it'd be something like getHostByName6 or something, but you can pass into this one. This one you pass in the actual type. So I believe we could have used this one for the IP version 6 as well, and it would have worked just fine as well, because we would have passed in the IP version. Sorry, the IP version 4.
Did they also write Duke 2?
Did they also write Duke 2? They probably also wrote Duke 2. Yes. Yes. If you ever build a big system, you will quickly realize that there are decisions you have to make that you hate at the core, in your core, but you have to make those decisions because it just happens that the way. Now, did they have to do it this way? Probably not. But there's some committee that probably decided that, and that's the way it goes. Anyway, let's see this program in action. Okay, I think it's already made. Let's see. Resolve hostname. Yes. Okay. So if we type a hostname, let's try www.stanford.edu. Okay, so it says that that's the actual host name, the official one. Now, it's a good thing we don't have to type that every time you want to go to www.stanford.edu. Why is it that big long one? Well, it tells you that actually Stanford relies on Amazon AWS services for their, well, if you think about it, it's actually not a terrible call. Why do it all in-house if you don't have to, right? Just rely on some giant company that has billions of servers out there, and it's probably going to stay up relatively often and so forth. I believe if we just type stanford.edu, we get, there we go, we get the official name is just stanford.edu, and it happens to go to a slightly different web address. My guess is that if you type www.stanford.edu, your browser may actually, let's try this. I'm going to try something. ping stanford.edu, okay, it says 171.67.215.200. Okay, so that's that. If we ping www, let's see what happens here. No, it's giving you the other one. So they're slightly different. They probably end up pointing to the same place somewhere along the line. But yeah, there's they do end up with different. www actually makes a slight difference in that case, but I bet if you type both, you'll end up at the same place. Somewhere along the line, they reroute it to the same web page. Let's try a couple more. Let's try google.com. Google.com has an IP address that I believe is actually based on your location. Like it kind of knows who's asking, and then it returns the IP address about like where, like locally, more local to you, as it turns out. Let's see, facebook.com. Yeah, same thing. There you go. What's some of the other ones? Let's see, www.facebook.com. There you go. So the www.stanford one, actually, I think it had two. There it is. It did have two different IP addresses associated with it. Those are Amazon addresses, I think. And then there's another one that Jerry likes to use, Okcupid.com. I don't know that Jerry likes to use that, but Jerry actually showed me this, that it has lots. I'm not sure why. And it's not because like billions and billions of people are using it and like Google has a few people here and there. So I don't know why. There's something going on where their host server says, hey, these are all your IP addresses, and it shows up in this list. And it's a little bit black magic after that. Now, GitHub.com, let me try it. GitHub.com. There's just one for that one. I could try www.github.com. Same. So it's the same. That one happened to be the official name was the same one, and it went to the same one. So yeah, there's definitely some black magic going on there, and I don't know all the details about that. So let's do one other thing. I want to show you just one other thing here. GDB. See, I told you it'd feel like 107. GDB resolve host name. Okay. Break on publish IP address info. I think is there we go. All right, let's run it again. Let's do stanford.edu. Actually, let's do the Okcupid one just to see what okcupid.com. Okay, so if we go into the code and we get the host name, okay, if we print out HE, it's just a pointer, right? If we print out host HE like that, it tells you all the details there. Okay, so the details there are, in this case, the name, that's just a pointer to the name, and then the aliases are in there. It turns out there's no aliases. I believe if we do, let's see, how are we going to do this? We're going to do star HE, let's do the star HE arrow H aliases. Let's see if that works. Yeah, so there are no aliases, as it turns out. And then, let's see, the address type happens to be 2 in that case. That one means the IP version 4. And then the length is 4 bytes, so we know how long the address is. And then the address list is, remember we said it was a char star, but if we just said try to do this, addr list, like that, it's going to be kind of garbagey, right? Because we don't really know what it is. I think you're going to have to actually do something like this. Let's see if this works. Let's see if we can do this. We're going to have to cast it. I know, it gets ugly, right? We have to cast it to a, what is it here? It is a struct inaddr. Struct inaddr star, maybe? Nope. It's going to be, nope, oh no. Let's see. I did this earlier. I figured this out earlier. Okay, that's that. Maybe we need to do, hang on, let's see. Is this going, hang on. This the only, like, this one? Yeah, it's going to be the, well, it's going to be the same thing. If I yeah, hang on. Okay, so that's that one. And then if we want to then, let's see. So let's print out what each one of those is. P0x84. Aha, 132. Was that one of the Okcupid ones? Ah, it is. 132. Okay. And then, let's see, 84, D0, 208. Yeah. What are the other ones? 208, 41, and 198. So we should get 41 should be 29, and then C6 should be 198. Okay, notice the order it's in, right? It's in the wrong order. It's backwards. Well, the function that we called earlier, that inet_ntop function, actually knows that it's in the wrong, knows that it's in little endian format, and then gives us the correct string back. Okay, but we haven't yet actually converted, like sent anything over the network yet. Yeah.
Does it know that it's little endian from being resident on the server or from the host?
Yeah, it knows that by the time it gets into that number, it's whatever the computer's representation is. So in this case, little endian. When we actually send it across the network, we have to turn it into a big endian number. You have to do that so that everybody knows how to. Why big and not little? Somebody made that decision. I mean, you know, it's a. So do you know where the little endian and big endian comes from? Oh, you guys need to take more. See, this is so supposedly Stanford is a liberal arts university. That's what I understand, but it comes from Gulliver's Travels. So in Gulliver's Travels, there were the little endians and the big endians who cracked their eggs either on the big end to open them up, or like their hard-boiled or soft-boiled eggs or whatever, or the little endian, and they got in a big fight over it. And so that whoever's creating this said, oh, it looks like the little end is there. They went, oh, I remember this. Oh, and this is also going to cause a big fight. And so that's why we get questions like, why, what does it matter, and so forth. So it was actually a perfect analogy, as it turns out. But that's where it comes from, as it turns out. Okay, so let's just, while we're at it, let's look at the hostname 6.cc, which is the, Vim. Resolve hostname 6.cc. Let's look at this one. We kind of looked at this one already a little bit. If we want to do IP version 6 addresses, we can actually look at them. We have to actually use a get host by name 2 and tell it we're looking for an INET 6 address. And then we have to check and make sure that's an INET 6 address or IP version 6 address. And then same sort of thing here. We can use this function. It knows how to convert IP version 6s. Let's see that one as we run it. Let's actually do it in DDB just to see the difference. Resolve hostname 6. Let's first run it and see. Hostname, google.com. There's google.com's address. Now, there's 128 bits here. This is a pretty big, 128 divided by 8 is 16. That would mean 16 various things. There's not 16 here. There's 1, 2, 3, 4, 5, 6, 7, basically 7, 8 because it takes them out, and then 9, 10, and there's little extra double colons in there. This is a decision they made to try to make the IP version 6 number smaller. If there's a bunch of zeros in a row, you can actually put 2 colons, and it just says, look, all the rest is zeros in there. I still think it's like almost impossible for a human to figure out exactly what all that means. It's not impossible, but it's just like you got to rack your brain about where's the zeros and how do they fit in, and it was probably an uninspired decision as far as I'm concerned. But some places actually, when they remember an IP version 6 address, there's 128 bits available, which is 2 to the 128th different addresses. Actually, let me go to here. I got the number in here. There it is. There are this many different IP addresses that you can now have. That number is bigger than the number of protons or atoms in the universe, I believe. So you will be able to assign every atom in the universe an IP version 6 if you'd like. So I doubt we'll run out of them, at least in our lifetimes. But you never know, I suppose. But they look at it. So if you're a big enough company and you have enough clout, you can actually ask for a particular IP version 6, and why would you care about that? Facebook.com. Take a look at Facebook's IP version 6 address. It actually says Facebook in it, which is like, oh, how clever, how nice is that? And, and again, I don't even know why they didn't put just 2 double colons there. Again, I don't understand how these things are figured out, but maybe someday they'll just have vanity IP addresses, and you can get one for your phone or whatever. Not that you actually care, but People at Facebook, I guess, care about these things. Let's just run it. Let's break on the same function as before. Publish IP address info, and then oh no, is it not there? Hang on, vim resolve hostname 6 cc. It is called let's see, publish, of course, publish IPv6 info. Let me do that. Okay. All right, break on that, and then run it, and yes, we're going to start it, and let's try Google again. Notice I didn't do Stanford. Wait, let me show you Stanford. Yes, stanford.edu, continue. Oh, I don't know if it has it yet, just kind of too bad. But anyway, that's the way that goes. Let's see, hostname, we'll try it again, google.com. Okay, google.com. Okay, so you do the get hostname, and then there, and then there, and then we have to cast it to this struct in address 6, and that we have to actually do that. So if we just type again, let's see, print out HE, it will give us the fact that it is got a length of 16 for the number of bytes and the actual address list and so forth. So there are some differences that go into that. Yeah, Hassan.
Why do you need to cast it as a struct in6 address ** if like you're able to do just address list ++?
Right. Good question. Take a look at the struct. Where'd it go? There it is. Okay, so this is cast to a char ***. It's not cast to what it really is, right? Why isn't it cast to really what it really is? Because we want this to be generic enough to work with both IPv4 and IPv6 and any other one that you want. There's actually another one that's IP. I think it's just got a. I think it's what is it here? It's not IN address. It's IN ADDR_UN, I think, for Unix, and it's its own type, meaning that you can use sockets like internal to a computer, and it's another way of doing that. So again, this server thing is pretty robust, but it's robust enough that there's some weird details in here that you kind of have to get to know. But does that make sense about that? Why you'd have to do that?
How come you're able to do it back in that code? How come you're able to do address list ++ there?
How come you were going to do address list ++? Yeah, you can do address list ++ because it knows now that it's this type of struct, right? Once you do that, if you didn't do that, it would try to do one character at a time, and it would get all screwed up. Again, 107 stuff. Yeah.
This might be a dumb question, but what happened to version 5?
I don't know what happened to version 5. I mean, that's a good question. This could be deadly, but what happened to the IPv5? Why is there no IP version? Yeah, it might be like Windows 9. Let's see. It doesn't exist, so there is no IP version 5. Let's see. It was intentionally skipped to avoid confusion. There was an experimental protocol called the Internet Stream Protocol, defined in 1190, and therefore it was assigned IP version 5. And we don't use that anymore, so they said, oh, let's skip it and use 6. Has nothing to do with there's 4 bytes or 6 bytes or anything like that, if that was one thing you were thinking. So that's that. Okay, no worries. All right, I know this stuff is definitely a bit crazy. So anyway, we've run a bunch of these here. Now, let's talk about the sockets themselves. Okay, when you are creating a socket, remember we had the accept command and we had the create socket and so forth. We are going to look at those in a little bit of detail to see how they're actually built. Okay, we're going to look at the create client socket and create server socket. Now remember, they are two very different things. When you are creating a client socket, what you are trying to do is you're trying to reach out to some other computer and connect to that computer's IP address and port. Okay, so you're trying to actually go, let me make a connection with some other computer. That's when you're creating the client socket. You're a client, you're trying to create the client socket. When you are a host, if you're trying to do the create server socket, all you need to do is get your local port number and try to assign it to yourself. We call that binding it. We'll see how that works. So you don't actually reach out and get anybody when you're doing a server side. You're basically saying, hey, I'm here. Please, I'm listening for people to connect to, for other computers to connect to me. That's the big difference there. Okay. Now, of course, we have different types of sockets here. This is also, again, where it gets a little bit hokey. Okay. We have a generic socket. Okay. The generic socket is struct sock address, and it has as its first element, its first member is this unsigned short called SA family. Okay, it's a 2-byte value called SA family, which is going to be which is going to say what protocol it is. Then we have a really bizarre SA data, 14 bytes worth, but that's it. Okay, it doesn't say anything else about that except that it says there's 14 bytes there. And you say, oh, well, all right, maybe that 14 bytes is going to be useful for something. I don't know, we'll see. Then we have struct sock address IN for internet, and this is the IP version 4 version, okay? And it also has as its first 2 bytes the family, the socket internet family, okay? And then it then has a port number associated with it, and then it has one of these struct IN addresses, which we saw earlier, sign ADDR, which says the actual 4-byte internet address in it. Okay, remember it's that weird, it's 4 bytes and not, it's actually a struct, which is weird. Okay, and then it has 8 bytes worth of zeros. And they're defined to be zeros, and it turns out they're completely ignored, although most people actually just do set them to 0 because it says 0 in the name, and so they figure, well, I should probably just set it to 0. It actually probably doesn't matter one bit. Okay, they're completely ignored. All right, so what does that mean? Well, I don't know, we'll see. Let's count the bytes first of all. Let's see if this actually does anything. How many bytes is a short? 2. Short's another 2, there's 4. How many bytes is an unsigned int, which is the IN address? 4, so that's 8 total. And then there's 8 more, so that's 16, right? And then up here we had 2 there and 14 there, so that's 16. Okay, that sounds like it might make sense. Let's look at the internet version 6 version. Okay, well, it also has the first 2 bytes as the family. Then it's got the first 2 bytes as the port. Remember, ports are only 2 bytes, either whether you're using IP version 6 or 4. And then it's got a struct IN6 address, and that's going to be SYN6 address. How big is 128 bytes? How big is 128 bits in bytes, rather? 16. 16 plus 4 is 20, plus 2 is 22, plus 2 is 24, plus another 4 is 28 for this one. Is that 16? No, I have no idea why this is the case. It turns out that it really doesn't matter that there's this 14-byte one there. I think there has to be something there to make the compilation work right, but that's about all I can figure out. The various resources I've looked at said, it just kind of doesn't matter. So, whatever.
Wait, what's flow info?
What's what?
Flow info?
Flow info and scope info, or scope ID. I'm not even sure what those are. Those are specific things to IP version 6. The nice thing about this thing is that it is generic enough so that you can have this that has extra stuff in it. Flow info might have something to do with the actual back and forth between the server and client, and maybe it's more efficient than something else, and they wanted to add it in there. Scope ID might be something else too. I just don't know. But it's beyond the scope of this class, no pun intended. But it's just extra information that goes along with it there. Okay, so that's what a sock address looks like. We've got this generic one, which doesn't seem to do much for us, except that it has its family in there. And then we've got these other ones that have the family as well as the first 2 bytes and then extra stuff in them. That's the important stuff. In fact, there's not just 2. There's this other Unix one, and there's other ones as well. Socket is a very generic type of structure. Okay. So that's that. And as I said, the version 6 one has some other stuff in it. Okay. The you will rarely ever declare variables that are of this type. Okay? This is kind of like an abstract class or something in Java or those sorts of things, where you've got this definition that you will never actually use. It's just there so that other things that kind of inherit from it can be used. Okay, so you will rarely ever do an actual struct sock ADDR. You'll do the one you want for the particular socket you're trying to create. Okay. And Linux actually does kind of one set for both because they want to make it generic. Okay? What you're going to have to do, and we'll see this when we actually write the code, is you are going to have to do some casting associated with these to get the right value out. Now, if you remember from CS 107, all of that casting you would have had to do when you did generic functions. There are times when you are, say, writing a function that has two void star pointers where you don't really know. You know when you're writing it, but the compiler has no idea what type it is because it expects void star pointers. You know, because you're the one writing the function, that, oh, really, these are char star pointers or something like that. Inside the function, you will actually cast them. It's going to be very similar when we go and figure out what these are. Okay, when we actually write these two functions we're about to write. Okay, all right. We are going to write two functions. One is create client socket. The other is create server socket. Okay, the create client socket's a little bit easier, even though it seems like there's more to do. You're actually trying to reach out to this other computer and connect to it, but there's not that much really to do. You know that you're going to know the port address or the port number and the address, and then you have to set up this socket to do it, and that's what we're going to do. Okay, what we're going to do is we are going to confirm that we can actually talk to the IP address. Okay, well, confirm that the IP address exists for that host. We're going to try to go to some host and we're going to go, look, we need the IP address. Let's see if it exists. Okay? Then we are going to allocate a new descriptor. This is exactly like, except very different from a regular old descriptor, file descriptor. It's just like a file descriptor in that it lives in the file descriptor table and it has an open file descriptor and so forth, but you don't use it in the same way. It's a two-way communications instead of a one-way, which most of our other descriptors were. Okay? You use this system call called socket to actually configure a socket descriptor. When you use socket, it doesn't actually talk to any other computer yet. It just sets up the socket so that you can populate it with the right details and then use it. Okay. Then we have to create an instance of sock address _in if we're doing IPv4. And then that packages up the host and port number. That packages all the details that we're going to connect to. We do that. And then now you've got this socket that you've set up. Now you can actually go and connect it to the other computer. Okay, that's what we're going to do. And then if all goes well, you return that socket to whatever program or whatever function requested it. Okay, question? Sam?
Conceptually, how is this different from just setting up a server and a client like we did a couple of years?
Yeah, good question. The question is conceptually, how is this different than setting up? Now we're doing the details of setting it up. So we actually called these functions before. Now we're actually going to go and dig in and go, what do they look like? And that's where all this other stuff that we had to get to is involved. Good question. A socket descriptor lives in the file descriptor table. The type is a socket. So it's not a read file, write only file, etc. It's a socket. And it's got more details associated with it because it needs to be two-way and potentially connect to other computers and so forth. But because pretty much everything in Unix is a file, they still made it a file, even though you can't use it quite like you would a normal file descriptor. Yeah. Okay. All right, let's actually do this. Okay, let's go and do this one now. Let's see, we want to do client sockets.cc. Okay, this one is here. You've also got this code so you can follow along as we do this. We're going to do struct host ent he equals get host by name, and then the name that we passed in, host.cstir, like that, which is exactly what we talked about for 10 minutes earlier, okay, because we're trying to just figure out if it's there, okay? All right, if HE is null, we're just going to return -1, which said, look, we didn't get it. We don't know what address you're talking about. And then hopefully whoever's calling create client circuit is paying attention to the return value and then knows, oops, I didn't get the socket that I requested. Okay. And then we do in s equals, and this is where we call the socket function to set up the socket. In this case, we're doing AF inet, and then we're doing sock stream. Okay, and then let me talk about that in a second. Sock stream is basically telling the operating system, please, please, please handle this the way the regular old internet works. And you might say, well, how does the regular old internet work? Well, I'm going to tell you. When you send data between two computers, you don't send one long stream of data like all at once until you're done. I mean, you kind of do. But what it's done, what happens in the way they've set it up is it's sent in packets. Okay, a packet can be various sizes. I think I'm not exactly sure how big a packet is right now. It might be something like 128 bytes or something like that. It's relatively small, but maybe it's 512. But it has information about the data. It has a packet number, and it has information about the data itself, and then it has some of that data. Okay. And you send a whole bunch of these packets off to some computer, and they all take different paths around the internet. Many of them go on the same path, because it just happens to be the shortest path, but it might not. And some of your packets may go down one path, some might go down another path, and they all meet up at the computer where they're trying to be heard, in the one you're sending them to. And they may end up in the wrong order. Okay? If they end up in the wrong order, it actually doesn't matter because the other computer is going, okay, I'm going to listen for all these packets. And if I get packet 2 first, I'm just going to hold it aside until I get packet 1. And then I'm going to know that I got packets 1 and 2. And I'm going to order them all when I get them. And sometimes packets get dropped. In fact, packets get dropped all the time. Some computer goes down or there's a glitch somewhere or whatever. If a packet gets lost, there's a timeout associated with that on both ends, as it turns out. When a receiving computer gets a packet, it sends an acknowledgement packet back. It says, I got your packet number 3, right? And then the sending computer goes, okay, packet 3 got through, and it checks it off the list. If the receiving computer doesn't get packet 3, it waits a little bit of time, and then sends it just waits, I believe. It just sits there and waits. It's the sending computer that says, oh, I never got an acknowledgement. I'd better send another packet, right? And it keeps sending them until it gets through. And that's sometimes why it can take your file, and that's sometimes why your file buffers and so forth. Question?
What if the acceptance packet gets lost?
Yeah, good question. That's such a good question. What if the acknowledgement packet gets lost? It's exactly the same thing. The sending computer says, oh, they never got my thing. They send another one. And then the receiving computer, if it gets 2 packet 3s, it ignores one of them. It ignores the second one because I already got it. Right? So it's robust in that sense. There is a problem called why am I blanking on it? Let me think about this for a second. Say again? No. There's the Byzantine emperor's problem. That's what it is. No, Byzantine general's problem. Again, liberal arts education. The Byzantine general's problem is what happens if there's 2 generals on 2 hills and they both want to coordinate attacking a valley, and they have to agree on the time they have to attack the valley. And let's say one general sends a message to the other general and says, we're going to attack at 7 a.m. And the other one sends a message back that says, okay, we know we're going to attack at 7. Well, what if then you never get those acknowledgments? And even if you do, how does the one who sent the acknowledgement know that the other one got the acknowledgement? And then so you can never quite exactly coordinate. So there's a little bit of an issue there. But generally, you send how many total bytes you want at the beginning, and hope that gets through, and you get an acknowledgement on that, and whatever. It turns out it works out okay, as it turns out. But that's how it works. So basically, you send a bunch of these packets on. Here's what sockstream does. Sockstream says to the operating system, please take care of all of the details of that packet back and forth for me. If you don't want the operating system to do that, let's say instead you wanted to handle it all yourself. You just want to send the packet and let them go in the order they're in and go and do that. there's more work for you to do, especially if you want to keep everything, like make sure that the other end got the package. You have to do all that. And you may want to do that. Let's say you're sending video data or something, and you don't care about every byte or every packet. Maybe you want to do that, you want to send it that way. You can say, hey, I'll take care of it, because it doesn't matter that every a few bytes of the video, maybe the video gets a little blurry for a second. Who cares? At least it continues, instead of having to be slowed down by this acknowledgement business and all that. So there are reasons to do that. We will only stick to sockstream in this case. All right. Okay, so that's that. If s is less than 0, again, that means we had a problem. Return -1. Okay. Now we have to do struct sock address in address, and we need to populate this address we're creating here, because we're actually going to use it to do the connection. So we are going to do this. Now the first thing we're going to do is memset %address 0 size of struct sock address in like that. Actually, I guess we can just do, that would probably work, but we could also just do size of address. I think both would work. We're doing that just to zero out the memory. Again, it probably doesn't matter as it turns out, but we just do it because it says, hey, these things should be zeroed. It's not actually a matter. I think we fill in all the bytes anyway, as it turns out. Okay, then we're going to do address.internet, basically socket internet family equals AF inet. And then we are going to do address.sign port equals. Now, here's where we need to make it into a network number. When we're going to set up the socket, we have to make sure that it's correct for the network order. I'm not even sure why they couldn't just make the connect thing do this, but you need to actually do the following. You need to say HTONS port. And that stands for, let's see, forget now. The host, host to network short. It's going to convert the port to the correct address. It's going to flip those 2 bytes, as it turns out. If you were building this on a big ending machine, that would be a no operation function. It would actually do nothing because it's already in that order. That's the way it goes. Okay, so we have to do that. All right. Oops. So then we have to, we're going to do the address sign address equals, okay. Ready for this? We have to now cast it appropriately, okay, we have to cast it to a struct internet addr, like that, addr. Why are we doing, oops, what did I do here? Hang on. Sign addr equals, there, did I forget the number of, yes, I did. I must have forgotten one there. There's one at the end. So now we are casting that 4-byte int we got to an actual struct to make sure it goes into the struct correctly. Why? Because it's a struct and not actually an int. That's the way it goes. Okay. So we do that. Okay. And then we call this connect function. Okay. If connect. Okay, we are passing in the socket that it has nothing associated with it yet. We're about to do that. Okay, we have another cast we have to do here. Struct sock address star. This is basically downcasting it. It's losing information in the big picture, right? It's losing information when you do this in the sense that the compiler is going to be looking for a sock address instead of a sock address in. Okay, all right. And you say, well, how do you ever get that information back? Well, let's talk about that. After you do this line, size of address and equals 0. That's the actual connect line. How does the the connect function know that we are doing internet version 4? That's the question. How does it know? What did we say was the same about every one of these? The first 2 bytes is always the address family, right? So if we know that the first 2 bytes are always in the address family, and we know that structs always have to be in the order of the members, we can actually look at that first member and say that member must be the type, and then inside the connect function goes, well, if the type is internet address 4, let's handle it this way. If it's 6, we'll handle it this way. If it's Unix, we'll handle it this way, etc. Okay, so it tells that by knowing what it is. Okay, all right. Okay, if that's that, return 0, meaning that return S, meaning that we actually got the correct socket.
Could you re-explain how it knows?
Yeah. Okay. How does it know? We are creating this up here, right? Now that is it's one of the types of internet address family setup, like structs, right? The first 2 bytes have to be, in fact, we set them here. The first 2 bytes are the family. So anytime you get one of these generic socket address ones, if you look at the first 2 bytes, it will be a family. And then you can say, oh, I know what the various families are, therefore it must be of this type, socket address IN, and therefore they treat it that way. So the connect function needs to know the different types. And it looks at the first 2 bytes, says, oh, that one's 2, or that one's 4, that one's 8, or whatever the different the number is, and then it decides internally, oh, I know what this is. That's how it does it. Now, you can't do that in C because you can't overload function declaration types, so therefore you had to do it this wonky way. CS107, yay. Right? That's what that all comes back to. Okay? All right. Now, if for some reason you don't get a connection, let's say the connection actually is broken or something, you have to close that socket that we created, right? Because we opened, or that descriptor, because we actually opened a descriptor using socket, and so therefore you have to close it. So if you get to this line, it means something's bad, and you need to close it, and then you return -1, like that. Question?
Yeah, so I noticed when we're setting the SIN address field, we don't need to do any endian converting.
Yeah.
Is that just a quirky thing?
I was hoping nobody would ask that question. The question is, and very good point. In this case, you don't have to do the endianness. I think because, let me think about this. Yeah, I'm not exactly sure. There's the reason, I don't know why you have to do it up here and you don't have to do it down here. I'm not 100% sure why. Yeah, I'm not sure. I'll look it up. I'll look it up and see. Yeah.
So this works.
This works. Yeah. Well, we can try it. I mean, it's worked for every example we've used so far in class, so I assume it works in that case. Okay, so what do we have? So that's the client connect function. Okay. All right, let's actually make it and see. Did anybody see any client socket? Let's see if that works. Hey, client socket. Okay. Oh no. I know why. Because it's not. It just needs to make it into a. If we just type make in this case, it would work because it's not. It's actually a library function that doesn't need a main function. So we don't have main in there. Okay. Any other questions on that? Yes. Why do we close it? If the call succeeds, we pass it back. The user needs to close it because you're setting up the socket, right? So down here, you're saying, let's actually connect to that computer and get, now the socket is an open file. It's an open file descriptor, or it's a connected file descriptor, I should say. And then you pass it back to the user who uses it.
And is that equivalent to how subprocess passes back the open FDS with the intent that the user will close the
Yeah. The question is that kind of like how subprocess passes back an open file descriptor, and the user has to close it? Exactly. Notice that we do close our descriptors when we're using them. It turns out the socket stream does the closing for us, but it closes it. Yeah, it does that. Good point. The using function needs to actually close it because it's the only one that knows when it's done. Okay, so let's now look quickly at the Serversocket file. Okay, this one's going to be somewhat similar, but we've got a couple extra little details to work on here. Okay, so in the create Serversocket, okay, we're going to do basically the same thing. And by the way, we're only doing Internet IPv4 in this case. AF inet, okay, sock stream 0, okay. So we don't need to get any IP address in this case because the IP address is our IP address, right? We're trying to set up a server on our computer, so it actually doesn't, turns out that it doesn't matter. We could use one of our IP addresses, and I say one of our IP addresses because your computer often has more than one IP address. If you've got Bluetooth, if you've got Wi-Fi, if you've got a cable, Ethernet cable plugged into your computer, you are going to have multiple IP addresses. So you can actually say only allow connections on this Wi-Fi or whatever, or as it turns out, you can say any, which we'll see in a second. Okay, all right, if that doesn't work, we are going to return -1. It didn't even open yet, so we don't need to actually close it. Okay, but if it did open, then we can go on and we can go, okay, struct, and same things before, sock address, in address. This is going to look relatively familiar. Okay, and then we're going to mem set address 0 size of address. Okay, and then we're going to set the sign for the family. And this is again how the socket function is going to, or in this case, the bind function is going to know how to interpret our downcasted address or downcasted sock address. Okay, so we're going to do that, and then sock sign family equals AF inet. Okay, and then we need to do address dot sign address dot address. Okay, in this case, now we do need to do this. So I'm wondering if we did need to do it before. No, I don't think we did because it always worked before. I'll look it up, see why this is. Okay, so what we're doing now, we are doing HTONL, meaning we're going to now convert the IP address that we are doing into host to network form, in this case. Okay, HTONL, INADDR, any. We could have put our own IP address, but we don't want to because we want to just, in this case, allow it to connect on any of the available ports. You don't have to do that if you don't want to. And then address.sign.port equals HTON short port, like that. Okay. And then now we need to make it so that we are connected to that port for the operating system, and we need to make it so that we're listening to that port. So we have to do two things. We have to do what we call bind. Okay, we bind the socket to the address. Okay, and again, you have to downcast it like follows, sock address. Okay. And then same thing. Okay. If bind equals 0, and let's do another thing called listen. The listen system call says, oh, okay, now that you've got this function, this port that you've bound to, now you actually say, oh, whenever I get somebody trying to connect, forward that along to my program. And you do that with the listen, okay? And then backlog. Did we type backlog there? Did we have backlog in there at all? Oh, it's passed in. Yeah, I'm not sure what I think that normally we pass that in as 0 or null or whatever. And it doesn't actually matter. Not sure what the backlog one actually does. Return S. Okay. So in other words, if you can't bind to the socket, and if you can bind to it, and you can listen to it, return that socket that we've now correctly set up to be a server socket. Okay. Otherwise, we close the socket because we had a problem, and we return -1. Okay. And that's how that works. Yeah, Bruno.
What is line 22?
what does line 22 do? Okay, that sets up the address that we are, it basically tells in this case, it tells the bind and listen function, you can listen on any of my IP addresses. That's what it means.
Is that different than any of its ports?
It is different than any of its ports because your computer has an IP address through the Wi-Fi. Your computer also, believe it or not, has an IP address through Bluetooth. And it also has one if you connect an Ethernet port in. So there's different IP addresses which are associated with the connection in this case. Okay. As it turns out, I believe IN any actually is 0, so you probably don't even need to do this at all. But that wasn't the case in the other one, so again, I'll look that up and what the other one is. And now we have set it up to start listening. What other questions? Yes?
I don't know if this question makes sense, but is there a way to like uniquely positionally find like an IP address to a socket? Like what prevents me from like being a client and requesting a socket and like making a copy of it and forwarding it to like a bunch of other servers or IP addresses?
Okay, so let's see about your question. Your question is, what's stopping the client from connecting and then reassigning things or whatever? So the client, remember the client it's a very opaque procedure. The client is a different computer that's trying to request something from the server, and it just says, hey, I want to talk to port 1234. And then if your server is listening to it, it just sets up a connection that says, okay, start giving me data for it. It doesn't do anything else locally on the other server computer. It can't reach over to the server computer and change any of the ports over there.
Yeah, but why can't it just communicate with like other computers?
Oh, it can try to communicate with other ports.
And like copy that to them and then those things can communicate.
Well, it can try to, well, okay. So it could try, let's say you send a random message to a web server on port 80, and you're trying to get information. It's only going to talk web. Like it has no other, it's not going to try, it's not going to be able, you're not going to be able to get any other information from it. You can take that and then pass that information to pass that to other programs and whatever, and then they can talk to the web server. It doesn't really matter in the sense that it's not going to, what you do on your computer with that socket is irrelevant. As long as you talk web HTTP, then it'll be fine. And maybe multiple programs can talk, sure, but it doesn't, maybe I'm misunderstanding your question.
I guess like I'm just trying, maybe this like doesn't make sense, but like can like a server be given a socket that it did not itself request directly?
Can a server be given a socket it's not requested directly, that hasn't been requested directly?
Like one hop away.
No, I can't. I mean, it's local to the machine. A socket is local to the machine. It happens to be maybe connecting to another machine on a particular IP address on the other machine, but that's it. Like there's no other. You can't request a socket. You can't request a port that's not listening, first of all, and you can't request anything that's. Stop by right after class. We'll chat. Come on back right after class and we'll chat. But anyway, any other questions on this? Sorry, but not good. Yeah.
Could you explain what the backlog does?
Yeah, I'm not 100% sure what the backlog does. Let's look it up. Bind. Bind. Let's see. Bind to a socket. Let's see. Bind. Was it bind? Hang on. It was. Oh, it was listen. Sorry. Listen for an action on a socket. Backlog. Okay. The backlog argument defines the maximum length to which the queue of pending connections may grow. So basically, if a connection request arrives, the queue is full, the client receives an error. Okay, yeah, so this is saying how many different connections you're going to allow. And I think the maximum is 128, actually. I don't think you're allowed to do more. But it's going to make it so that your program can take a little bit of time to set up a connection, and then the operating system will keep a backlog of the other connections and then forward them to you one at a time. I believe that's what it is. Yeah.
I'm just getting a little confused on the differences between a socket, a port, and IP.
Yeah, good question. Okay, so the question is, I'm getting confused about port, socket, and IP address. Okay, an IP address, let's start with the reverse order. An IP address is your computer's address that the rest of the world knows about. Okay? my IP address on this machine, on Myth64 rather's IP address, ifconfig gives you the IP address, and it's right here. The IPv4 address is 171.64.15.29. The IP version 6 address is this big long one here, and the scope, there's where the scope comes in. It's a link for some reason. So that's where your IP address is. It's the address the rest of the world talks on. When somebody from the rest of the world wants to talk to you, they can ask for a particular port of yours that one of your programs is listening on. So maybe we want to SSH into Myth. That's port 22. So we go look at IP address, and then we look at port 22, and that gives us an SSH connection. If we look for port 80, that gives us a web connection. If we look for port 443, that's a mail connection or something like that. So that's what the port is. It's defined as of your IP address, like on your computer, what port are you listening to for various types of things. Now, a socket is the file descriptor that is associated with a connection either to another computer or one you're listening on. The socket itself is the file descriptor that you can read and write from. And you can do both, as it turns out. Does that help answer your question? Yeah, good. Yes,
So if you have multiple other computers around the world that are connected to listening to a certain port of yours, then there would be it would be one port but multiple different sockets. Because the sockets
Good question. So yeah, this is a very good question. I haven't really talked about this yet. The question is, wait, so we've got, if multiple computers are trying to talk to you on a particular port, does that mean they all have different sockets? Here's what really happens, and we kind of glossed over this. Once you set up a connection to another computer, you actually do it on a completely different port. The only thing you do on the original port is listen for connections. Then you set up another port to go and connect to the client through another port that you can listen on and do the connection on. So once you set up on that initial port, then you actually hand over the connection to a different port to have that connection. So let's say you have 1,000 different computers connected to you. You will then have 1,000 other ports that they're connecting on and talking back and forth, and you're still listening to port 80 for the next connection to come in. That's what happens there. Good question. Yeah?
Since socket is a type of file descriptors and threads share file descriptors, does that mean that when you want to listen on multiple ports, you have to do processes? Because then you can show the file descriptor.
When you want to listen to various ports, you have to do processes? Not really. I mean, you can listen to multiple ports in a particular process, just like you can have multiple files open.
I guess my question is, do threads share sockets?
Oh, do threads share sockets? Yeah, I believe they do. Yes, I believe threads share sockets. Now, it's not really going to, again, when, like in your thread pool for networking, for instance, when we do that, we set up a new connection that's a different port when we do all this, when we do set up the connection back to the client. It's a different port altogether. Yeah. Okay. Any other questions? All right. We will see you all Wednesday.